Imagine you are standing on a glass floor over a void that stretches down forever. You feel solid, the glass feels real, and the air you breathe seems certain. But then a physicist taps you on the shoulder and whispers that according to our best calculations, the glass shouldn't exist. The floor is actually 95% something we can't even see, and the passage of time is just a stubborn illusion. We like to think that modern science has the universe figured out, that we are just filling in the minor details of a nearly complete map. But the truth is much more unsettling. There are deep, fundamental cracks in our understanding of reality, mysteries so profound that they keep the world's most brilliant minds awake at night. These aren't just academic puzzles. They are existential glitches that suggest our entire perception of the cosmos might be fundamentally wrong. We are going to explore the 7 physics problems that terrify scientists, from the invisible ghost matter that dictates the fate of galaxies to the horrifying possibility that the universe is basically a ticking time bomb waiting to disintegrate. If you thought the universe was a predictable clockwork machine, prepare to have that certainty dismantled. Let's start with the big one. When you look up at the night sky, you see stars, planets, and nebulae. This is baryonic matter, the stuff made of atoms, the stuff that makes up your body, your house, and every gold bar on the planet. But here's the problem. When astronomers measure the gravity in galaxies, they find that there isn't nearly enough visible stuff to hold them together. Galaxies are spinning so fast that they should be flying apart like mud off a rotating tire. There has to be some invisible extra mass providing the gravitational glue. We call it dark matter, but we have absolutely no idea what it is. It doesn't emit light, it doesn't reflect light, and it doesn't block light. It passes through you, the Earth, and the Sun as if we weren't even there. But it gets worse. In the late 90s, scientists discovered that the expansion of the universe isn't slowing down under the weight of gravity. It's actually speeding up. Something is pushing space itself apart. A mysterious pressure we call dark energy. Combined, dark matter and dark energy make up about 95% of everything in existence. That means everything we have ever studied, every law of physics we have ever written, only applies to a tiny 5% sliver of reality. We are like sailors trying to understand the ocean while only being able to see the foam on top of the waves. The terror for physicists is the realization that we might be missing the most important part of the story, and our current telescopes might never be able to see the actors that are actually running the show. Moving on to the second nightmare, the hierarchy problem. This one is for the fans of fundamental forces. Why is gravity so incredibly weak? You might think gravity is powerful because it keeps planets in orbit, but compared to the other forces of nature, like electromagnetism or the strong nuclear force, gravity is a total weakling. Think about it. You can pick up a paperclip with a tiny kitchen magnet. That little magnet is successfully defying the gravitational pull of the entire planet Earth. Why? According to our standard models, all these forces should be roughly on the same scale. The fact that gravity is 10 followed by 32 zeros times weaker than the weak nuclear force suggests that something is fundamentally off. It's as if you found a mountain where the boulders weighed as much as feathers for no apparent reason. To fix this, scientists have to fine-tune their equations to an absurd degree, sometimes up to 30 decimal places. In science, when you have to fudge the numbers that much just to make the math work, it usually means you don't actually understand what is happening. It suggests there might be extra dimensions or hidden particles we haven't found yet. Or worse, that our universe is just a freak accident of mathematical improbability. The third problem is one that hits close to home for anyone interested in space exploration. Vacuum metastability event, often called the false vacuum scenario. This is the ultimate cosmic exit button. Quantum field theory suggests that the vacuum of space isn't actually empty, it's filled with energy. Scientists suspect that our current state of the universe might not be the most stable one possible. It might be a false vacuum. Imagine a ball sitting in a slight dip on the side of a mountain. It feels stable, but if you give it a tiny nudge, it will roll down to the very bottom of the valley, a state of lower energy. If our universe is in a false vacuum, a high-energy event, like a particularly powerful cosmic ray collision, could trigger a bubble of true vacuum. This bubble would expand at the speed of light, and inside this bubble, the laws of physics would be completely different. Atoms might not hold together. Gravity might work differently. Since the bubble travels at light speed, we wouldn't see it coming. 1 second you are drinking coffee, and the next, the very fabric of space-time is rewritten, and you, along with the Earth, the Sun, and the stars, Simply cease to be what you are. Physicists are terrified because they can't prove this won't happen. In fact, based on the mass of the Higgs boson discovered a few years ago, the math suggests we might actually be living in such a precarious state. The universe might literally be a giant bubble waiting to pop. Fourth on the list is the black hole information paradox. This is a battle between the two greatest pillars of physics, general relativity and quantum mechanics. Relativity says that anything that falls into a black hole is gone forever, crushed into a singularity. Quantum mechanics, however, has a golden rule. Information can never be destroyed. If you burn a book, you could theoretically reconstruct the text if you tracked every atom and photon of smoke and ash. But Stephen Hawking discovered that black holes eventually evaporate through something called Hawking radiation. If a black hole disappears, what happens to the information about everything that fell inside? If that information is gone, it breaks the laws of quantum mechanics. If it's not gone, it breaks relativity. Scientists have been fighting over this for 40 years because the stakes are the very consistency of physics itself. If information can truly be lost, then the past might not lead to the future in a predictable way. The universe would become fundamentally lawless at its most basic level. The fifth problem is the mystery of antimatter. According to the Big Bang Theory, the start of the universe should have produced equal amounts of matter and antimatter. When matter and antimatter meet, they annihilate each other in a flash of pure energy. If the amounts were equal, they should have all canceled out, leaving a universe filled with nothing but light. No stars, no planets, no people. But clearly we are here. For some reason, there was a tiny excess of matter, about one extra particle of matter for every billion particles of antimatter. Why? What caused this asymmetry? Scientists have searched for a tiny bias in the laws of physics that favors matter, but so far the results are inconclusive. It's as if the universe cheated at the very beginning to allow us to exist. This CP violation is a major headache because it implies that the fundamental symmetry we expect in nature is broken in a way we don't understand. We are the survivors of a cosmic massacre we can't explain. Sixth, we have the problem of time. If you look at the equations of general relativity, time is a dimension, much like up, down, left, and right. It's part of the static fabric of space-time. But in quantum mechanics, time is an external clock that ticks away outside the system. When you try to combine relativity and quantum mechanics into a single theory of everything, time often disappears from the equations entirely. This leads to the Wheeler-DeWitt equation, which describes a universe that is completely frozen, like a photograph. This is terrifying because our entire experience of life is based on the arrow of time, the idea that the past is different from the future. If time is just an emergent property or a trick of perspective, then our sense of cause and effect might be a total delusion. Some physicists suggest that we are living in a block universe, where every moment, past, present, and future, exists simultaneously. Your birth, your first job, and your final breath are all there, laid out like points on a map. This challenges our very concept of free will. If the future is already written into the geometry of space-time, are we just actors following a script we can't see? Finally, the seventh problem is the cosmological constant problem, often called the worst prediction in the history of physics. When scientists use quantum field theory to calculate the energy of empty space, they get a number. When astronomers measure the actual expansion of the universe to see how much energy is really there, they get another number. The difference between the two is a factor of 10 to the power of 120. That is a 1 followed by 120 zeros. To give you an idea of how big that error is, it's like trying to measure the width of an atom and being off by the size of the entire observable universe. This discrepancy suggests that our understanding of how quantum things, the very small, interact with gravity, the very large, is not just slightly wrong, it is catastrophically incorrect. It's the smoking gun that tells us our standard model of physics is an incomplete story, and we might be standing on the edge of a scientific revolution that will change everything. For the investors and space enthusiasts listening, these problems aren't just curiosities. They define the limits of what we can do as a species. If we can't solve the problem of gravity, we might never find a way to manipulate it for faster-than-light travel. If we don't understand dark matter, we might be blind to vast resources or energy sources that could power a galactic civilization. The physics of the future depends on solving these glitches today. We are in a race to understand the code of the universe before we hit a limit we can't overcome. Consider the financial implications of dark matter detection. the first person or group to identify the WIMP or axion, the theoretical particles of dark matter, will essentially own the secret to 80% of the universe's mass. This is the ultimate intellectual property. It's like being the first person to discover that electricity exists. It could lead to entirely new industries, new forms of communication, or even new ways to map and navigate deep space. The space economy of 2026 and beyond might be driven by the hunt for these shadow assets. This is why governments and private donors are pouring billions into massive underground detectors and space-based observatories. They are hunting for the ghosts that run the cosmos. But let's get back to the terror. Why does this scare scientists? Because scientists are seekers of truth, and these 7 problems suggest that the truth might be stranger than we are capable of imagining. We are biological creatures evolved to find fruit in trees and avoid predators on the savannah. Our brains weren't designed to comprehend 11-dimensional strings or quantum superposition. There is a very real fear that we might hit a cognitive wall. Perhaps the universe is so complex that the human mind simply cannot grasp the final equations. This is the end of science fear. The idea that we might reach a point where we have all the data, but no one is smart enough to see the pattern. Black holes are particularly scary in this context because they are the laboratories of these problems. Inside a black hole, the forces of gravity and the quantum world are crashed together. If we want to solve the information paradox or the cosmological constant problem, we have to look inside the event horizon. But the event horizon is a one-way door. The universe has censored its most interesting secrets. This cosmic censorship hypothesis suggests that nature is actively hiding the evidence of its own contradictions from us. It's like being in a room with a locked chest that contains the meaning of life, but knowing that the moment you open it, you are trapped in the chest forever. Then there is the thread of fine-tuning. If any of the fundamental constants of physics, like the strength of gravity or the mass of an electron, were off by just a fraction of a percent, stars wouldn't form or atoms would fly apart. This leads to the anthropic principle. Is our universe so perfectly tuned for life because there are billions of other failed universes in a vast multiverse, and we just happen to be in the lucky one? This terrifies many scientists because it moves physics away from being a hard science where we can predict everything to a soft science of probability and luck. It suggests that there might not be a reason why things are the way they are. It's just a cosmic survivor bias. Think about the implications for the future of humanity. If we are living in a false vacuum, our entire history, every war, every masterpiece, every scientific discovery could be erased in a heartbeat by a quantum fluctuating bubble. It underlines the fragility of our existence. We are living on a tiny planet, orbiting a middle-aged star, in a universe that might be inherently unstable. This realization can be paralyzing. But for many, it's a call to action. It emphasizes the importance of space exploration. If the universe is a high-stakes environment, we need to be as spread out and as knowledgeable as possible. We need to become cosmic engineers rather than just passengers. For the finance-motivated listeners, consider the energy potential of the vacuum. If we could tap into even a fraction of the zero-point energy that the cosmological constant problem describes, we would have a source of power that makes nuclear fusion look like a candle flame. We would have enough energy to terraform planets, move moons, and launch missions to other stars. The energy crisis would be solved forever. But the gap between our current tech and vacuum energy is measured by those 7 terrifying problems. Solving them is the key to the next stage of human evolution. Now let's talk about the fine structure constant. This is a number that governs how light and matter interact. It is roughly 1/137. Physicists like Richard Feynman were obsessed with it. Why that number? It's not pi, it's not e. It's just 1 divided by 137. If this number changes even slightly in different parts of the universe, as some controversial studies suggest, then the laws of physics are not universal. They might be local rules, like the laws of a city rather than the laws of a kingdom. This would mean that a spaceship traveling to a distant galaxy might find that its engines don't work, or its crew's biology starts to fail because the local constants are different. This puts a geographical limit on how far we can explore. The 6th problem, the problem of time, also opens up the possibility of time travel, or the impossibility of it. If time is just a static dimension, then now has no special meaning. The year 1920 is just as real as the year 2024. This suggests that wormholes or Alcubierre drives might not just move us through space, but through time as well. But this creates the grandfather paradox. If you go back and prevent your own birth, how can you exist to go back? The fact that we haven't been visited by time travelers from the future, that we know of, is a terrifying data point. It either means time travel is impossible, or it means that civilizations don't survive long enough to invent it. This is a variation of the Fermi paradox, and it adds another layer of anxiety to the study of high-level physics. Let's look at the Schrödinger's cat problem on a cosmic scale. In quantum mechanics, things exist in a state of superposition, being in two states at once, until they are observed. This works for atoms, but does it work for the whole universe? Who is observing the universe to keep it real? This led to the many worlds interpretation, the idea that every time a quantum event happens, the universe splits into two. If this is true, there are an infinite number of yous out there. In one universe, you are a billionaire space tycoon. In another, you didn't survive a childhood illness. This is terrifying because it means our choices might be meaningless. Every choice is made, somewhere, in some branch of the multiverse. It strips away the uniqueness of our reality. The problem of dark matter also forces us to rethink our place in the food chain. If 95% of the universe's energy doesn't interact with us, could there be dark life? Could there be entire dark civilizations living in the same space as us, using dark matter to build their cities and dark energy to power their craft, completely unaware of our existence, or simply not caring about the invisible fleas, us, that live in the visible dust? The idea that we are not just alone, but essentially irrelevant to the bulk of the universe's activity, is a profound blow to our collective ego. Science is often portrayed as a steady march toward enlightenment, but these 7 problems show that it's more like a climb up a mountain in a fog. Every time we think we see the summit, the fog clears a bit and shows us an even higher peak. The terror for physicists is that the mountain might not have a summit at all. It might just be an endless climb of increasing complexity. But this is also what makes physics the most exciting field in the world. Each of these problems is a door. Behind one of them is the secret to everything. As we move toward the year 2026, we are launching new missions like the Euclid Telescope and the Nancy Grace Roman Space Telescope. These are our reconnaissance missions to tackle dark energy and dark matter. We are building the High Luminosity Large Hadron Collider to hunt for the hierarchy problem's hidden particles. We are on the verge of new data that could solve these problems or make them even more terrifying. We live in the era where we might finally find out if the vacuum is false, if time is an illusion, and if we are just a tiny 5% mistake in a dark universe. So when you look at the stars tonight, don't just see the light. Think about the 95% of the universe that is invisible and pushing those stars away. Think about the fragile vacuum in which they float. Think about the information trapped in the black holes at their centers. These 7 problems are the boundaries of our island of knowledge in a dark, mysterious ocean. They are scary, yes, but they are also the reason we keep exploring, keep questioning, and keep looking up. Because the only thing more terrifying than these problems would be a universe that was so simple that there were no mysteries left to solve. The complexity of the universe is a testament to its grandeur, and our struggle to understand it is the greatest adventure of the human spirit. Stay curious, space enthusiasts. The universe is waiting to be solved. Whether we find a theory of everything, or simply discover that we need a bigger shovel to dig into reality, the journey is what matters. Those 7 problems aren't just obstacles. They are the signposts pointing toward a future we can't even imagine. Keep your mind open, keep your sensors tuned, and remember that in the world of high-level physics, the most terrifying thing you can find is also the most beautiful, the truth. It's a long road to 2026 and beyond, and the cosmic glitches are just getting started. Let's see what we find when we finally dare to look the universe in the eye.